Hi, everybody. Hope you all can hear me. And I'm just going to wait, just a moment, maybe another minute. And I think we have some more people we're expecting to join the webinar. So we'll get started here in just a minute. All right, don't want to delay it too much longer, so I think it's a good time to get started. Hi, everybody. Welcome to National Hydrologic Warning Council's monthly webinar series. Thank you for joining. Today, our presenter is Mark Moore. He'll be speaking about pressure transducer and tipping bucket calibration. All right, and if you have any questions, please place them in the questions or the chat. And Mark said he's happy to answer questions during the presentation, or we can wait until afterwards as well. So with that, I will pass over control to Mark, and he will start the presentation.
All right, good morning and or afternoon, everyone. Thanks, Matt, for getting things started for us. My name is Mark Moore. I work for Distinctive AFWS Designs. We're going to be talking today a little bit about calibrating pressure transducers and tipping buckets. This is a talk that's been requested by a few different groups, and this is really meant to be an introduction to the conversation about calibration. As I worked on this, I realized I started to make a presentation about PTs, and then I kind of started to make a presentation about rain gauges, but what I really want to focus on is the actual calibration. So I'm going to try to spend as much time talking about actually calibrating things, and not necessarily spending a lot of time talking about tipping buckets and pressure transducers. As Matt mentioned, at any point, do feel free to step in, ask a question, put something in the chat, and I will happily answer that as we're going along or save it for the end. And I also just want to give a heads up. I'm currently in a hotel room in Fort Worth right now, which means that a lot of what I have is set up on the desk, things pulled from my truck. So it might be a little more scattered than we usually prefer to do things, but that's what makes this job fun. So without further ado, I'm going to go ahead and get started. And like I said, if you have questions, just speak up. So first off, the overview. What are we going to talk about? Well, I promised I wasn't going to talk too much about pressure transducers, but we've got to have a little bit of conversation there. So we are going to talk a little bit about what are pressure transducers. Then we'll talk about why do we calibrate, discuss a little bit about the difference between a calibration and an accuracy test. Then we'll talk about tipping bucket calibrations and pressure transducer calibrations. Quick disclaimer, you can read what it says, but basically I have various hardware on my desk right now. You're going to see various software that I use for these calibrations. It's really not meant to endorse any of the equipment. It's really just whatever I had in my truck that I wanted to show you guys. So it's really just an example. And just because I'm showing you a certain manufacturer's pressure transducer does not mean it's the only one, does not mean it's the best, does not mean it's the worst. It's just the one that I had available for this test. So again, don't take any of this as a, this is the way to do it with only this one software or hardware solution. Some quick terms to know, because I don't like to have abbreviations in there without at least discussing them. I will very frequently say PT. When I started my job, one of the first things they told me in my interview was a PT is a pressure transducer, and get used to hearing PTs. So again, I will probably go back and refer to PTs as PTs instead of pressure transducers, but it's the same thing. It's a sensor that's used to measure pressure, and it relates that to a depth of water. You might see ADC come up a little bit. ADC is an analog to digital converter. It's what takes something like a voltage and makes it something we can see from a data logger. And then V is volts. It's often used as the output of the sensor, but it's certainly not the only thing that can come out. So what is a pressure transducer? Well, as I kind of just mentioned, they're sensors that respond to a change in pressure with some sort of signal output. So if you guys have ever worked with PTs or pressure transducers, you've probably seen them before. And this is showing a little bit of what's on the market today of different brands and solutions and PTs out there. But all of these are pressure transducers. So how do they work? Well, they're under pressure. A common, but certainly not the only way you can measure it, is with something called a piezoelectric crystal, which is not going to be on any exam, don't worry. But a piezoelectric crystal is basically a little sensor in a way in these pressure transducers that actually has a change of its electrical properties when pressure is placed upon it. So I'm not sure if my mouse is completely visible here, but you've got the pressure pushing down on that diaphragm of that PT, and when it pushes on the diaphragm, it pushes on the actual crystal, which has that electrical change and can be monitored and related to water level. There's kind of an issue with that, and that's, PTs are measuring all of the pressure. A PT isn't just measuring how much water pressure is on it. A PT is actually measuring the water pressure and the atmospheric pressure above it. And so when we take these measurements from pressure transducers, something we have to be aware of is that we want to make sure we're canceling out the changes of the atmospheric pressure. And there's two ways you can do that. One way is you can actually put a vent tube behind the diaphragm, and that way any atmospheric pressure that comes from one side is canceled out by atmospheric pressure on the other side. Another way to do that is to actually have a separate barometric pressure sensor close to your gauge or inside your gauge, and then you can do that on your data logger and actually subtract the atmospheric pressure from whatever your pressure transducer read. So taking a quick step back and looking at this previous slide, with a pressure transducer, as I mentioned, that pressure is both water and atmospheric pressure. And so the most common way that you see this negated is by adding a vent line, which comes in on the other side of the diaphragm and helps cancel out that atmospheric pressure. And the reason that I'm being a little bit of a stickler about this is that vent tube, that vent line that goes behind the diaphragm and pushes back, it has to be kept clear. It has to be kept dry, and it has to be kept unbent, undamaged, and accessible. And that's why with a lot of pressure transducers, you see those vent tubes come out into some sort of desiccant box or a desiccant tube. And that keeps that vent tube nice and dry so you don't have condensation in it, which would block the pressure transducer's vent tube and cause it to get bad data. But this isn't a talk about pressure transducers, as I promised, so I'm not really going to harp too much more about keeping your desiccant fresh. This is a talk about calibration. So why do we calibrate? Well, at the end of the day, we calibrate to produce a useful output, because a lot of these sensors aren't actually saying it's 10 feet of water. They might actually put something out there that's like 2 volts or 15 milliamps or 0.18 psi. What we care about is the depth of the water with pressure transducers. And what we care about with tipping buckets is the inches of rain. Just saying that it tipped once doesn't mean anything unless we know how many inches are in each tip. So why do we calibrate? Primarily, it's to produce a useful output so that our flood warning systems are actually sending data, because you can't put on your public facing website that the water level rose 0.197 psi. People aren't going to know what that means. What we want to say is that the water level rose 2 feet. But there's other advantages to calibration as well. They can help correct baseline drift. It helps confirm that you have a linear output, which we'll talk about in a little bit. It demonstrates functionality at full scale, and I want to take a moment and focus on that real quick, because that's a really nice advantage when we're talking about calibration, especially when it comes to PTs and bubblers when they allow for it, is that we know after we calibrate that our sensor is going to work the entire range that we calibrated across. You're sitting there on a day that it's not flooding and you are testing your stuff and you're hoping that it works when the water's high. But a calibration is really, when you're testing that. And when you calibrate it up to 20 feet and you get good trustable data, you can be confident that when the water level is actually 20 feet deep, that it's going to be accurate. So it's a really nice feature to be able to demonstrate that it works at full scale. I am a big proponent of radars, but one of the issues you could say maybe with radars is you can't really calibrate them across the range. That'd be something that have to be done back in the lab with very expensive high-tech equipment. You are hoping that it works when the water goes up. And again, I'm a big fan of radars. I'm not saying that's a bad thing, but one of the nice things about pressure transducers is that you can test yourself that it works when the water goes up. And last, you can also compare it to historical performance. You know, how long has the PT been accurate? Are we seeing a drift of it being less accurate, more accurate, etc.? So when we're talking about measuring stuff with calibrations, the first thing you have is some sort of force, a state, or an event. It could be a tipping bucket that tips, or, you know, realistically, it's rainfall that falls from the sky or water level that goes up. And we sense that. But we can't just say, you know, it rained. We have to turn that into some sort of electrical signal. And so that happens through signal processing. With a tipping bucket, it might be a magnet across a reed switch. With a PT, that might be changing that force, that pressure, into a voltage. Then we want to actually see what happened. So we have to, you know, convert it back into something digital that our data loggers can read. And that's where that analog to digital converter comes in. So we have the signal that's, you know, maybe 0 to 5 volts, and we turn it back into something meaningful, like 10 feet, 15 feet of water. We've now done data processing, and then we store it locally. Maybe we display it, or we transport it away. We send it through some sort of wire. Maybe it's a, you know, a gauge on a dam that's connected straight to the network. Or oftentimes we're talking about radios. So we've got, you know, an alert 2 site set up to transmit this, or it's cell radio, or any type of way to send it, or even a fiber optic line. So there are various ways that we can actually send this information. And you might be sitting there and thinking, all right, Mark, that's great, but, you know, we have SDI 12 PTs. We're not worried about 0 to 5 voltages or 4 to 20 milliamps. This is still the same process that occurs with an SDI 12 PT, where it's putting out a digital output. What's happening is that all of this sensing, signal processing, and data processing is happening in the PT itself. And so you still want to calibrate those devices because you still have the same things going on. Some of it's just behind the scenes. So here are just some examples of things you might see where you have a phenomenon or property that's occurring, the sensor, and then the electrical signal that's used for that. So for example, a pressure transducer is using a piezoelectric sensor and putting out an analog voltage. A temperature sensor is doing a thermistor, and that would also be read by an analog voltage. And I'm going to skip a few, but just ones you can see. Towards the bottom, you also see a rain amount, which is using a tipping bucket, which the signal is a contact closure. So again, calibration. How do we go from an electrical signal, say 1.432 volts, to something meaningful? We do that through calibration, somewhat. So what is calibration? You know, the meat and potatoes of our talk. Why are we talking today? What is calibration? Is doing a reference check to see if a tipping bucket meets the manufacturer's error specifications is an accuracy test calibration. What about determining the slope and offset of an analog sensor? Is adjusting the slope and offset to match a known good standard a calibration? Well, you know, if we're going to be honest, depending on who you talk to, any of these can be calibrations. Now, typically, scientifically, the calibration is adjusting the slope and offset to match a known good standard and determining the slope and offset of a current sensor. But you will often see agencies refer to things like accuracy tests as calibration. And we'll see that a lot with tipping buckets. You know, what is calibration of a tipping bucket? Well, realistically, calibration of a tipping bucket is changing these adjustment screws you can see in this diagram, up or down, to adjust the rate at which that bucket tips. Anything else is really more of an accuracy test than a calibration. And that's not to say accuracy tests aren't important, but I just want to make sure we're using good terminology when we're talking about calibrations versus accuracy tests. So if you haven't seen one of these diagrams before, this is showing you how a tipping bucket works. You've got a funnel that brings in the water. Usually there's a much bigger funnel with screens over this. And you've got a bucket that can go back and forth. And as it pivots, this little magnet and magnet arm move past our reed switch, and that generates a signal that's picked up by a tipping bucket data logger. So it's just really counting 1, 2, 3, 4 every time it tips. Those screws that you can see on the bottom, those adjustment screws, can be moved up or down. And if you were to move those screws up, you can see from this diagram that moving the screws up would actually cause the tipping bucket to tip a little bit sooner. And so you'd have the ability to, adjust your tipping bucket. If it's tipping too late, if it's under reporting rainfall, you can fix that by changing those adjustment screws and actually having it tip a little bit sooner. This is just a picture of the same thing, but I wanted you guys to see what they actually look like instead of just a diagram. So if we want to know if a tipping bucket's accurate, one of the first things we can do is figure out how much is in a tip. So for the tipping bucket in that previous photo and the one that I've got on my bench that we're going to work with in just a few minutes, the first thing we're going to do is figure out how much rain is in a single tip, how much rain is supposed to be in a single tip. So I promise I'm not going to do too much math because no one wants to see math presentations either. But if you think about it, a tipping bucket is collecting a certain amount of rainfall, and that rainfall has a depth based on however much a single tip is. So say you have a tipping bucket that's 0.04 inches, which is what we've got right here on our bench and what we've got in this previous picture. This tipping bucket is actually a 1 millimeter tipping bucket, but it's often reported as 0.04 inches of rain. So that means for every 1 millimeter of rainfall, it's going to tip once. Well, we can then see exactly how much volume is in that by thinking of it as a cylinder of water that's been collected by this funnel. So the funnel is a 12-inch diameter funnel. And the equation for a cylinder, if you remember geometry, is V is equal to pi r squared times the height. Well, I've already translated it to centimeters for you guys, and both the radius and the height. And we're not going to do the math together because I'm just going to push the button and see what it is. So you get about 72.96 centimeters cubed, or for easier numbers to follow, about 73 milliliters of water in each tip. Well, we can use that to do a static calibration, or maybe more accurately said, a static accuracy test. We know how much is supposed to tip in each bucket, and we can use a syringe on each side of that to make sure that it's working the way it should. Then we could adjust those calibration screws until it's getting exactly 73 milliliters in each tip on each side of the bucket. There are some problems with static calibrations. For example, it doesn't account for the fact that you lose a certain amount of rainfall when the bucket's tipping. And so if you've got old bearings in there, it's not caring about how long it takes between tips. All it's caring about is how much rain does it take to tip. It's not going to tell you anything if your funnel's clogged or if you've got a stuck switch. A static calibration does not depend on rainfall. And this is a little graphic I found from a study that was kind of showing different tipping buckets and how accurate they are at different rainfall rates. And once you start hitting 200 millimeters of rainfall an hour, you start to fall pretty far behind that 1-to-1 line. You would hope that the measured and the reference at 200 millimeters per hour of rainfall are the same. But you can see most tipping buckets actually start to fall below that 1-to-1 ratio because of the fact that they lose rain as they're tipping during high rainfall rates. Again, that's more of a tipping bucket talk than a calibration talk, but something to be aware of. And then the last thing about static calibrations is that they're incredibly difficult to do in a field. Oftentimes tipping buckets are up in the air, 10, 15 feet up. You're on a ladder, it's a windy day, the bucket's shaking, a big truck drives past, and it tips sooner than you're expecting it to. So this is something that's usually reserved for the bench, not done in the field. But I wanted to go ahead and show you guys, an example of a static calibration. So give me just a moment. I'm going to change over my webcam. You might get a quick glimpse of my face before we get the tipping bucket loaded. All right, so if everything's going the way I hope it is, you guys have pretty clear view of a tipping bucket on the screen.
Yep, we can see the tipping bucket.
Great, thank you. So to do a static calibration, we're going to put exactly, you know, we're going to measure exactly how many milliliters of water it takes for this bucket to tip. And we'll do it on either side. I'll tell you right now, if I were a responsible presentation giver, I would have already done this for the tipping bucket and have the answer prepared for you. But I'll be honest with you guys and say that I have not done a static calibration on this bucket. So we'll see what we get. It'll be an interesting group experience. I've already leveled the tipping bucket, so we have an idea. It has to be leveled for a static calibration or any type of calibration to be worthwhile. So the tipping bucket's already leveled, and we'll go ahead and get started. So give me just a second to walk over there, double check that it's level, adjust it a little bit. While I've got this tipping bucket here, one thing I wanted to show is that I talked about that if this reed switch gets stuck, that doesn't always show up in a static calibration, but it would show up in a dynamic calibration. And that can happen sometimes during installation, or, you know, say you were doing some maintenance and you accidentally grab the bucket like that. Well, what happens is when it tries to tip, it gets stuck. You know, this tipping bucket should have clunked, but it didn't, because this switch right here is too close to that little reed switch. And it can actually get stuck halfway in between. And that won't always show up on a static calibration, and it should show up on a dynamic calibration. But just one thing to be aware of is that you want to make sure that that arm is far enough away that it can move smoothly back and forth, but not so far away that it's not picked up by your data logger. I will be using a graduated cylinder. I hope this isn't too close to the camera. You can see I put so far about 70 milliliters worth of water in here, which, depending on this tipping bucket, may or may not be too much water. So let's see what happens. Okay, so with 70 milliliters, we have not yet tipped. We shouldn't. We should tip at 73. What I'm going to do is I'm going to finish it off with this syringe, and we'll be able to count exactly when it tipped from there. And I'm going slow because I want to get it as close to the milliliter mark as possible. All right, so we just tipped. I'm coming back over to the computer, so give me just a moment. So that tip took about 75 milliliters. And if you remember from our previous math, it should have been closer to, you know, 73 milliliters. And if we wanted to, we could actually then adjust these screws down here and make it so that that bolt sticks up a little bit higher and it tips a little bit sooner. One thing to be aware of is that which side it tips on is based off of the opposite bolt. So this side is going to tip down based on the position of this bolt. And this side is going to tip down based on the position of that bolt. So that's how you do a static calibration. You'd actually compare both sides of that bucket, try to get it as close as possible to what should be 73 milliliters, and then follow it up with a dynamic calibration, which is what we're going to talk about next. I'll give just a few moments if anyone has any immediate questions, but again, we'll kind of keep going about rain gauges from there. As I adjust my camera back to our presentation. All right. So a dynamic calibration. The dynamic calibration is going to say, okay, rather than just do one tip, let's do multiple tips. And the question immediately asks here on the slide of how many tips would 1,100 milliliters have? And there's a reason that we're using that number, and you should see my camera again with the presentation. The reason is because we're going to be doing it with an Nalgene. And this Nalgene fills up to 1,000 milliliters, but all the way to the top is actually 1,100 milliliters. So the question is how many tips would 1,100 milliliters have? Well, we'll take that 1,100 milliliters and divide it by 73. And what we end up with is 15 tips with 4 milliliters left over. So if we put this amount through the tipping bucket and the tipping bucket is working perfectly, we'd expect it to tip 15 times and we'd expect it to have 4 milliliters remaining. Any more left over and that tipping bucket is over-reporting. Less than 15 tips and the tipping bucket is under-reporting. If we put that amount of water through the tipping bucket and we're expecting it to tip 15 times, but it only tipped 14 times, well, guess what? We're not tipping as much as we should be. And then we can use that information to adjust those set screws until we get closer to what we expect to get. One thing to be aware of is that this does depend on the rainfall rate. So I kind of brushed against this earlier. And again, I promise not to talk too much about tipping buckets, so I'll be brief. But when the tipping bucket is tipping, it starts to move. And during this tip, it's still collecting rainfall into the wrong bucket. So for the first half the tip, rain is falling on the wrong side. And the heavier the rain is, the more rain falls on the wrong side of the bucket. So when it's raining very heavily, you get less accurate rainfall collection from a tipping bucket. During a dynamic calibration, we know that the rainfall rate can be determined based off of, the type of bucket you've got. And I didn't do the math here because I've done it before with these tipping buckets. These are High Sierra 1 millimeter tipping buckets that we're using in this example. Each tip is 1 millimeter of rain or 0.04 inches of rain. And if you do the math, there's 3,600 seconds in an hour. So 2 inches of rain an hour would be a tip every, and it would be 50 tips an hour, which ends up being 1 tip every 72 seconds. And that only applies for our buckets we're talking about today. That only applies for a 12-inch diameter collection funnel that's measuring 0.04 inches of rain per tip. But what we can actually do is we can then take 144 divided by the tip time and get the rainfall rate from that. So I'm going to show you guys how we do a dynamic calibration. And I don't think we're actually going to run through the whole thing, but I want to show the process of what we do and how we can find out if our tipping buckets are working the way we hope they are. So let me stop sharing my screen real fast and go back to, ideally, the full camera screen. I'm going to move the camera back a little bit to give a better view of both this beautiful hotel art we've got, but also how we calibrate. So first off, we're going to use this PVC adapter. Now there are also commercial solutions on the market. This is just what we've been using with our company. Some agencies use something similar, but you can buy off-the-shelf parts to do just this. What this is going to do is it's going to keep the water level constant because the water is not going to go above or below this when we're running it through. Then we've got a very small hole in the bottom of it, and water is going to go through that hole, through the tipping bucket, and we'll know exactly how much, rain's falling through it. I've also got this Nalgene, as we talked about earlier. Now this Nalgene has 1,101.2 milliliters of water. We measure that using a scale. And we're gonna use this Nalgene with this calibrator together on the tipping bucket, and we'll see how many tips we get. Give me just a moment while I set that up. And we want to make sure this is level and going straight into the funnel. So moving the camera just a little bit so you can see the full setup. We've got water coming through this calibrator into this tipping bucket. And we're really expecting to get 15 tips with just a little bit left over. We might get a little bit more, we might get a little bit less, but we'll see what we find. So first tip should be happening in just a moment. There it goes. It's about a 15-minute process, and it'd be a pretty boring webinar if I sat here for 15 minutes and watched this go. So my plan is to kind of let this run in the background Hopefully not annoy everyone too much with the clings and clangs as it tips, but continue talking about calibrations and how we do things. So again, this is going to take about 10 to 15 minutes to run through, and it should be about 15 tips. We'll leave the camera on so you can see both the calibration happening and the presentation. So one thing to be aware of for calibrations, and if you've seen any trainings that I've done, you've heard me say this a lot, read the specs. Anytime you're calibrating, and it doesn't matter if it's a tipping bucket, a pressure transducer, a bubbler, a radar, a soil moisture sensor, your accuracy has to be based off of the specifications of the sensor. You know, we can't say that this tipping bucket has to be accurate to within 0.5% if the specs only say it's accurate to within 3%. We have to match our expectations to what the specifications of the sensor are. So this is a screenshot from a tipping bucket calibration spec sheet. And you can see that the measurement uncertainty is 1.0% up to 2 inches an hour. So it should be accurate to 1% error, but that's only assuming it's raining less than 2 inches an hour. That might be a little hard for people to conceptualize, so let me kind of give the example. You know, 2 inches an hour is about when you're on the highway and you're getting a little nervous that, man, it's raining so hard, maybe it's about time I pull off the highway. Places like Gulf Coast regions can easily see, you know, 4, 5, 6 times 2 inches an hour. But the idea is that 2 inches an hour is a pretty significant rainfall rate. And if you're getting that much rain, it's pretty heavy. And this example of this specification sheet says that it's 1% accurate up to 2 inches in an hour.
Hey, Mark.
Yeah.
We have a question. Ben Pratt asks, what is the recommended frequency for both static and dynamic calibration?
Yeah, thanks, Ben. So how often do we calibrate, specifically with tipping buckets? You know, it somewhat depends on the needs and the goals of your system. But a general baseline is to say, do a static calibration anytime you bring a rain gauge into the test bench, and do dynamic calibrations in the field about every 6 months. Typically with flood warning systems, you're going out every 6 months or so just because those funnels are going to clog. And those funnels are going to clog with leaves or bird poop or dust, construction debris. And if you're out there cleaning tipping bucket funnels and cleaning the screens and keeping everything neat and orderly anyway, it's a good time to go ahead and do a calibration. So generally speaking, my recommendation is dynamic calibration every 6 months, static calibration anytime you bring the tipping bucket in from the field. Again, I don't really think there's a lot of worth in doing static calibration in the field because it's just too many other factors that are going to make that bucket tip too soon. That's a test bench only thing. Now, there might be some agencies that want to calibrate before a monsoon season or before a hurricane season, but that still typically falls within about an every 6 month period. Thanks, Ben. So, you know, I've given 2 examples on my webcam, what I call a static calibration and what I've done so far is a dynamic calibration, but I haven't actually calibrated it. You know, I haven't adjusted the set screws to make it more accurate. And that would be the true full calibration, would be looking at the error from both a static and a dynamic, adjusting those set screws, retesting it, and getting that error as close to 0 as possible. That would take 30 minutes to an hour for just one tipping bucket, depending on how well it was behaving. So we're not going to do that for this presentation. But I just wanted you guys to see the steps that would take. We'd get our error, and then we would adjust these screws to make it more accurate if need be. Now, I'll also say that for the most part, if you're out in the field, and, you know, again, depends on manufacturer specifications, but if you're out in the field and you get an accuracy within 3%, I think that's pretty decent for a field calibration. If you're talking about something that you've got on your test bench like this, where there's no wind, there's no chance of drizzle, there's no big trucks driving past, it's worth it to work on that to get it to 1%. So while this keeps going, we're going to take a quick step to talk about pressure transducers as well, because those are the other things we typically calibrate in this field. And I just said this, but we're going to read the specs. So we can only calibrate to specifications. Again, I pulled this off of a website for this pressure transducer, and this is a fun one to say. The combined nonlinearity, hysteresis, and repeatability is plus or minus 0.1% FS BSL for all ranges. Boy, that makes sense, right? All right, let's take that apart real quick. Combined nonlinearity, hysteresis, and repeatability. Well, that just means that it's combined error. We'll talk about what those mean in just a second, but that just means it's combined error. It's plus or minus 0.1% FS. FS stands for full scale. So it's plus or minus 0.1% of the full range of the PT. And BSL stands for best straight line for all ranges, which is really just saying it's combining that nonlinearity, hysteresis, and repeatability. So what this is actually saying is that it's 0.1% of the range of the PT, and that's how accurate it is. Well, that means you have to pick the right PT for your system. 0.1% full scale of 20 feet is 0.02. So if you have PTs in your system that are 20-foot range PTs, and they have 0.1% full scale error, well then, their error should be within 0.02 feet. But say you said, you know what, I want my PTs to be able to read water depth up to 100 feet because that's what my system is and that's what I want to be able to make it do. Okay, well just be aware that if your full scale range is 100 feet, 0.1% of that is a tenth of a foot. So they're going to be less accurate because you have a higher range. So when you're buying your PT, that's usually one of the questions you get asked is what range PT do you want? And you don't necessarily want to pick the biggest range because it's going to give you more error. Alternatively, you don't want a 5-foot PT if the water level can get 20 feet deep because it's not going to work after 5 feet. So you have to pick your middle ground. You want to pick something that covers the full range of your system, but also is low enough that you don't get a very high error.
Hey, Mark.
Go ahead.
We have a couple questions about the tipping bucket calibration.
Yeah.
Joshua Krennick asks, assuming your nylon stopper does not move, how does a tipping bucket fall out of calibration?
Yeah, so tipping buckets can fall out of calibrations by a few different methods. Typically, it will be things like if it's very dirty, which is why you would clean a tipping bucket before calibration. Those bearings, they just start to age. So as the tipping bucket basically ages out, they'll start to be not as smooth. And this dynamic calibration will show that it's not as accurate as it used to be. The other thing is those nylon stoppers should stay still, but as we talked about, sometimes these are on bridges which are vibrating and bouncing, and so that can have an impact there. But usually it's more the tipping mechanism itself that's causing it to go out of calibration if those nylon stoppers aren't moving.
Okay, and then we have a question from Edward Reyes. He asked, will you provide a parts list to manufacture the calibration device?
Sure, yeah, no, I'd be happy to send that along. I'll either include it in some email to the attendees list, or if that doesn't go out, also feel free to reach out to me directly and I'll share what goes into building this calibration, or also I'll include a couple of the solutions out there that vendors have pre-built ones too. Any other questions?
That's all I'm seeing for now.
Okay, appreciate that, thank you. So one thing to be aware of for units is that most PTs are gonna be measured as PSI. And you know, 1 PSI is 2.3067 feet at 4 degrees Celsius, or 2.3106 feet at 20 degrees Celsius. Again, I promise not too much math, and I promise no exams. So don't feel like you have to know this number. But the most interesting thing to me that we're talking about here is that the pressure of water changes based on its temperature. And so if it's colder water, you know, it's going to be slightly more dense, and you get a smaller amount of water per unit of pressure. Whereas hotter water is slightly less dense, and so you get less water per unit pressure. And so when we're using pressure transducers to go from something like pressure to something like water depth, the temperature of the water is actually pretty important. And, you know, for these PTs, pretty much anyone out there on the market is going to have a temperature compensator in there. to adjust for this because it's 0.17% different. And we're only allowed 0.1% full scale error. So that would throw us out of accuracy if we didn't account for temperature changes. Just something I wanted to put out there and something to be aware of. So a quick summary of PTs is that most PTs provide a differential reading, a voltage, a 4 to 20, or an SDI12. Those are different ways they send the data. But at the end of the day, all of these examples are converting pressure to a signal back to a pressure reading and should be calibrated. When you calibrate, you're going to get a slope, an offset, and an error. So here are some things you might see. You know, what would cause a PT to be out of calibration? Well, one thing that temperature can do is it can have what's called a null shift error. And so the relationship between the voltage and the pressure can shift. Basically, it's offset. So the line, the slope is the same, but the actual up and down position of it, that offset, is dependent on temperature. On the other hand, you can have a sensitivity shift, which is the opposite. The offset is the same on all these tests, but maybe when it's colder or warmer, the slope changes. And so you won't have the same results at different temperatures when you really are expecting it to. So one thing you have to be aware of is these null shift and sensitivity changes. And when I say be aware of, it's more, you know, when you do these calibrations, this might be a reason your calibrations are showing bad data. This might be a reason that a PT fails its calibration, is because there's some sort of null shift that's not being accounted for because something on the PT itself has failed. I promised earlier I'd talk about hysteresis, linearity, and repeatability. Again, I'll try to be brief here. But hysteresis is basically saying that is the relationship between the output signal and the actual pressure on the PT the same going up as it is going down. If you are familiar with discharge rating curves, which is the relationship between stage and flow at a creek, you also have to consider hysteresis, because as the water level goes up versus the water level going down, you actually see different measured flows at the same stage elevation based on if it's going up or down. You can see that with the PT as well. You can see a different output if the water or if the pressure is going up versus the pressure going down at the same pressure because of hysteresis effects. Repeatability is pretty straightforward. It just says if we do the test again and again and again, do we get the same answer? We hope yes, but it's never going to be 100% perfect. Linearity says that we are applying a slope and offset equation from our Algebra 1 classes back in high school. So we're assuming that the PT has a straight line between its pressure and its voltage output or its SDI12 output or whatever it happens to be. This is never really the case. It's always slightly not linear, but we want it to be as close to a straight line as possible. For, you know, all of these conditions, if you remember, the 0.1% full scale error was taking all of these under consideration. So when we do calibrations and we're expecting it to get within 0.1% of full scale, you know, it's accounting for this hysteresis and the fact that it's not perfectly linear. And so all of that's included in the error already. So, you know, how do we actually calibrate? Now we know why, now we know what can impact it. How do we actually do it? How do we calibrate? Well, we're going to compare an output, a voltage, a current, or an SDI12 data to a known good standard. We're going to record that slope, offset, and standard error. We're going to update our data logger or software for the new slope and offset, and we're going to compare this to previous calibrations. I said known good, and I want to take a moment to focus on that a little bit. The PT specifications that I showed you was 0.1% full scale error. Our known good we're going to use today in our example has specifications as shown on the right, and we'll look at the total uncertainty. Our total uncertainty for this calibration tool we'll use is 0.025% full scale. So our calibration device is actually, in this case, you know, 5 times more accurate than our PT. And that's how we can calibrate, because we're taking something we know is very accurate, our PT calibrator, and we're going to use that to simulate pressure against our PT. One other thing to be aware of is that it says that the total uncertainty is 0.025% full scale. for 1 year. If you have a PT calibrator, typically it's in your truck or it's in your office and it's getting moved around and it's in hot environments and cold environments, heating, freezing, etc. The manufacturers really recommend that you take your calibrator and get it recalibrated once a year or so, because otherwise, you're comparing all of your PTs to something that's never been checked in 5 years, 10 years. Are you really doing any type of calibration if your known good isn't known to be good? That's a whole lot of words for calibration. So let's go ahead and actually do a PT calibration and just kind of see what we get out of it. So first off, I'm going to stop sharing my screen. Go back to our tipping bucket, which I'll take a quick moment to show that we got to 14 tips. It should have been 15 tips. So we get that out of the way. We're slightly underreported. We should have been at 15 tips, but we only got 14 tips. So before I do this pressure transducer test, we'll kind of finish off this rain one. We'll see how many milliliters it takes to get to 15 tips. Quite a bit. So that was 10 right there. All right. So that was about 29 milliliters shy of 15 tips. So we're about 35 milliliters behind what we should be, because it should have been 15 tips and 6 milliliters, and we're actually 14 tips and 29 shy. And so we could do the math on that to look at the percent error, and we would see that this tipping bucket, has actually failed its calibration. Now, again, this is straight from a storage unit, so it hasn't been fully cleaned, vetted, and set up. I'm not terribly surprised it failed, but it should have been closer to 15 tips and it wasn't. So good example there. All right, moving on to the PT calibration. So the calibrator we're going to be using today is a Druck DPI611. That's the specification sheet that I showed you guys earlier. And I'm going to try to adjust the camera so that you can see it. See how well this works. I know it's not going to be easy to see because I need to pump it from basically the bottom of it. But I've got the calibrator set up with PT right here hooked up to it. And right now you can see I've got 8.83, 8.81. It's dropping a little bit, feet of water on it. So when you're doing a pressure calibration, the first thing you're going to do is open this up with this calibrator, and it's going to drop that pressure to 0. So what we want to do is zero this out, because there's no pressure on it, so it should be reading exactly 0. What it's actually reading is 0.002 feet, pretty close to 0, but not exactly. So for this one, you hit the settings, you hit 0, you hit this button. There's a lot of buttons to push. You hit yes, and it zeroed it. Every PT calibrator is going to have a different way to zero it, but that's just something you have to do with any PT calibrator, is you zero it out before you start. Now I'm going to close this off, and I'm going to apply pressure. And I'm going to go up to about 20 feet or so. I don't have a great seal right now, probably because it's been on it for about an hour, and I'm in my hotel room. But you can see that PT is dropping by about 1/10 of a foot a second or so. I'm going to load up my screen. We're going to actually see the data from this PT and what it actually means. And I apologize that I don't have a way to make this screen bigger, so you're going to have to bear with me a little bit. What I'm going to do, let me clear this out. is I'm going to take measurements. This is an SDI12 PT in case you can't tell by the fact that it just said SDI12. I'm going to take measurements exactly when this PT calibrator reaches a level that I'm going to record. I'm going to try to show camera as well. See if it shows my face first. Oh, it does show my face first. It's lovely. Hi, everyone. Oh, it won't let me. Okay. Well, we're going to have to just use the camera that you guys can see for what the calibrator is at right now. So I'm going to clear this out. Now I'm going to take a measurement. So again, not an SDI12 talk, and every device is different. And if we're doing a voltage measurement, we might be doing it with a multimeter or looking at data tables on our data loggers or some sort of comparison. So the process for getting the data is very dependent on your PT. But for an SDI12, we issue a 1M command, 1M bang, or 0M bang, because that's the sensor address. And at the time, that calibrator was reading 19.244. To get the data from it, the output was 5.8557. You know, all right, that's a little strange. We would expect it to be close to 19 feet. It's an SDI12 PT, but we're only getting 5.85 something. Well, let's keep calibrating. Let's see what we get. So I'm going to lower this pressure a little bit. I'm going to take another measurement. We're about 17.4 feet in case you can't see it. So I took it at 17.393. And the PT put out 5.2. All right, interesting. So we're still a little low. Well, let's keep going down a little bit more. So we took a measurement at 13.758. I can type 13.758. And the response from the sensor when our calibrator was at 13.758 was 4.1854. Okay, we're starting to see a pattern here. Everything's off, but it seems to be off by a certain specific amount. I'm going to drop it a little bit more substantially now. We'll put it somewhere around 8 feet. Not bad. That was a pretty close guess. So we're currently at 7.669. 7.669. And that puts out some sort of output that is 2.33553. We'll do one more. We'll do two more. So we're at 5.9. Let the PT take a measurement. It was at 5.96. And the response was 1.814. And lastly, drop it all the way down, get it close to about half of a foot, take our last measurement. And our last value was 0.11. All right, I'm going to move this to full screen so you can see this. This is just an Excel sheet that does the math for us. So it takes our input, which was the readings off of our calibrator. Screen went dim, let me bring that up. It takes the input, which was the readings off our calibrator, takes the output, which is what the PT was putting out, and it gives us our slope, offset, and standard error. So in this case, our slope was 3.28. So for every 1 unit that came out of the PT, we would actually need to multiply it by 3.2869332 to get it to feet. And the offset was minus 0.002. Now what's interesting is look at the standard error of this calibration. The specification says that the standard error is less than 0.1% of the full scale, which if this is a 20-foot PT, would mean 0.02 feet. What we're actually finding is that across the range of this PT, it's accurate to 0.003. It's almost 10 times better than the specs say. So it's accurate to within 0.003 of a foot, up to 20 feet deep. That's good. I mean, that's as good as PT is going to get. And this is a new one. It's off the shelf. It's not been in the field, so we really should see it be low. But that's still great to see. So I'll give you guys a chance to look at this without me talking for just a moment. Think about, why was it not putting it out in feet? Shouldn't this be 19.24 is equal to 19.24? What was going on? Well, the answer was I changed the units of the PT. So the PT wasn't set to put it out in feet. The PT was set to put it out in some sort of other unit. And so because of that, it made it not a one-to-one relationship. Now, the standard error was still fine. It was still a great PT. If this were the case in your data logger, you just have to change the slope from 1 to 3.28. However, realistically, if you've got a site like this and you've got a data logger, just program the PT the right way. And for this specific brand of PT, the command would be 0xp05. Now it's in feet. So if I were to pump this up to, we'll put it 12, 11 or so feet, take another measurement. We were at 11.87 feet and it read 11.85 feet. So there we go. That's what's going on. It was just set for something other than feet. Once I set it back to feet, we can see we're pretty much right on the mark. So this is how we would do a calibration, and this is something we do in the field. Anytime we're working with a PT, you want to do at least 6 measurements, and you want to test the full scale. So if your PT goes up to 50 feet, you want to calibrate it to 50 feet. If your PT only goes to 10 feet, you want to calibrate it to 10 feet. But what you do is you do 6 points, you compare it to your known good, and with your known good, you can calculate a slope, offset, and standard error. And you don't need to see that calibrator anymore because it's not as interesting to look at. So one thing you can do with this is that, all right, we found the slope, but you can actually track that over time too. Every time you're up there, every 6 months, you are getting a slope, and that's something that you can record. Go ahead, Matt.
Are we supposed to see your slides?
Yes, thank you.
I'm looking at the calibrator.
Wrong button. Thank you, Matt.
Okay.
So this is, a site or a group of sites that was visited every 6 months. And when you're tracking this information, you can track the slopes to see, all right, are my slopes remaining constant over time, or are they drifting up or down? Or, in this case, during one of the site visits, every slope went up. Well, maybe if every slope goes up, it's not something with the PTs, it's something with the calibrator that was used. That's why it's important to track things like PT slope, PT offsets, standard errors. But when you're tracking that, also track what calibrator was used. Because if you find out 6 months later that one of your calibrators was in need of calibration itself, you want to know what sites were visited and go and correct that. And then you can also track things like standard error. Do things suddenly change, or is it a gradual change? You can track the offset. The idea behind calibration is 2 things. 1, is your sensor accurate? Is it good? Is it meeting the specifications? And 2, what are the slope and offsets used to make it something useful? And how are you keeping an eye on that to make sure that things stay standard the way they should be? So that was a whole lot that I squeezed into an hour, kind of at lightning pace. I'm not necessarily, as I said, expecting all of it to be, testable after having these conversations, but I wanted to show both how we calibrate and why we calibrate. If there's any specific questions, regarding procedures, how we do things, I'd be happy to share that. I'll also share with anyone who attended, a quick parts list and procedures list for how we did both calibrations, because just seeing it once isn't really enough. But I wanted to show the gist of how we calibrate and why we calibrate and kind of, what we can get out of it. So with all that said, I know we're right at the hour. I will take any questions.
We have one. Keith Hume asks, what equipment was used to apply pressure to the pressure transducer?
Yeah, great question. So I used, let me try to adjust my camera and not awkwardly show off half the hotel kitchen. Make this a little bit bigger. I used this device. Oh, sorry, I know it's cramped on this table, which is a Druck DPI 611. It was one of their newer models of calibrators, but all it really is it's a PT with a screen, but it's a really, really, really accurate PT with a screen that you can use to reference pressure. And then on the bottom of it, which is why I've had some issues showing it all on camera, you've got a pump that can pump up pressure. You've got a fine-tune adjustment, and you've got a pressure relief valve. Any other questions? All right. Well, if there's nothing else, I appreciate you guys taking the time. As I said, we'll be setting up some follow-up information. And if there's any questions you guys have, or you need a repeat, or something didn't make sense, do feel free to reach out to me, because this is something, in case you can't tell, I am pretty passionate about. I like to see sensors work to the best of their abilities. So I'm happy to have any conversations you guys want to have about how we do things and how we calibrate and how we make sure that our data is the highest quality it can be. All right, hearing no other questions, thank you everyone very much for attending, and look forward to our next webinar, which is going to be a month from now. It's going to be the last Wednesday of April, and it's going to be talking about antennas and how we work with those. So thank you very much, everyone. Take care.
Thank you, Mark. Bye, everybody.